so now we're at the third section of the syllabus, which is about waves. All right, so let's get into it. So waves, first we need to know what a wave is. So a wave is basically a disturbance that transfers energy without the medium moving, right? So it's just caused by vibration of particles, right? That allows the energy to be transferred from one point to a next without the medium itself that it's traveling through moving, right? So we have two types or two categories of waves. So it's either a mechanical wave or it's an electromagnetic wave. All right, so we're going to first look at mechanical waves. Right, so with mechanical waves, these waves require a medium in order for it to travel, for these waves to be produced. So it requires particles, right? So it's not able to be transferred through vacuum. So mechanical waves requires particles for these waves to be produced. All right, so we know we have two types of mechanical waves, which are magnetic waves, the transverse waves, sorry, and longitudinal waves. All right, so those are the two types of mechanical waves that exist, the transverse waves as well as the longitudinal waves. So let's look at each. So before we look at each individual waves, on a wave, right? So just one section of a wave, which includes just a peak of a wave or a trough of a wave, that's known as a pulse, right? So one single disturbance in a wave is known as a pulse. So a wave is created by attaching different pulses together. Right, so we have the two types of waves. So transverse waves. So transverse wave is a wave in which the vibration of the particles in the medium is at right angle to the direction in propagation of the wave. So that means if the wave is going in this direction, the particles in the wave will be vibrating up and down. Right, so that's right angle to the direction in which it's going. Right, so that's what a transverse wave is. While a longitudinal wave is a wave in which the particles vibrate parallel to the direction in which the wave is traveling. So the wave is going like this, the particles in the wave will be going back and forth like this. All right, so examples also of transverse waves. So waves that go up and down like these, such as light waves, water waves. Right, so all those waves are examples of transverse. The only longitudinal wave that CXC requires for you to know is sound wave. Right, so sound wave is the popular wave, common wave that is longitudinal waveform. Right, so on a wave, we need to identify certain things on a wave. All right, so the first part is the amplitude of the wave. So the amplitude of the wave is the maximum displacement from the undisturbed or the equilibrium position of that wave. So that means if the wave is going up and down at directly in the center of that wave, that's the equilibrium position or the undisturbed position. So the amplitude will be from that point in the wave to the maximum point that the wave will go up or will go down. So that's your amplitude of your wave, which is sometimes abbreviated as a capital A. Now the wavelength of a wave, it is the distance between 2 points which are in phase on the wave, right? Most books will have it that it's the distance between the two successive crests or two successive troughs, but it's not just crest or trough. It can be any point on the wave, but those 2 points have to be in phase. And in phase means that the particles, the direction in which the particles are vibrating the energy towards are the same. All right, so it's the two successive points that are in phase. That means their direction of vibration of the energy is going in the same direction, and they have to be adjacent to each other on each pulse. All right, and we're going to look at that on a diagram. The period of a wave tells us the time it takes for one wavelength to be created, right? So it's the time taken for one wavelength to be created on a wave, and the frequency tells us it's the number of waves passing a point every second, right? So frequency is measured in hertz, period is measured in seconds, right? So the wave number is not important at this level. We look at the velocity, which is the speed of the wave, which tells you how fast the wave is moving, which can be calculated by v is equal to lambda, which is the wavelength, times f, which is your frequency. All right, so let's look at this transverse wave and let's identify certain things from it. All right, so we see here that this is our undisturbed position in the center of the wave. All right, so therefore from this point to the maximum point there, that's your amplitude, or it could be this as well. So those 2 points will be the same value, and these are your amplitude of the wave. All right, now we notice that the wavelength, which is this lambda sign here, is from this crest to the adjacent crest on the wave. All right, but let's say we don't want to use those values. All right, so let's say we want to identify a particle here. So let's call this particle X. Right? So we notice that the wave is going to the right. So that means particle X will be transferring the energy in that wave in that motion upwards towards the crest, right? So if we want to find another point in which it will be a full wavelength for X, would be, it should be in the same line, so continuing that same line going across. If we look at this point here, right, then this will cause the energy to be going down, right? So therefore, that is not an in-phase point. So we continue going over and we reach this point here. And at this point, the energy in the wave will be going up towards a crest right there. So that means X here, and we label this one Y. Those two X and Y points will be in phase because they're transferring the energy in the same direction, and they're horizontally in the same position on the wave. All right, so is that clear on how to find the wavelength on a wave? All right, great. All right, so those two things are important when it comes to a wave. And also to note, because this is a transverse wave, if we have a point or a particle on the wave, if it asks you to show the direction in which they vibrate, because the wave is going to the right, we note that these particles will be going up and down. So directional vibration will be up and down to create a perpendicular angle between the vibration and the direction in which the wave is going. All right, so that's about the transverse wave. And also on a transverse wave, we have two terms, which are the crest, which is the maximum point on your above the undisturbed position, and your trough, which is the maximum point below your undisturbed position. So this is your trough, and this is your crest. All right, so those two terms are important as well. All right, so let's look at the diagram for a longitudinal wave. So our longitudinal wave, instead of a crest and a trough, we have two terms here, which are the refraction and the compression. All right, so we have the refraction here, the rarefaction, which tells us that this is the part where the particles are actually spacing out, right? And the area that the lines are closer together, these are known as the compression section, right? So this is where the particles come closer together, right? Compress, and then they separate from each other, where that is known as the rarefaction. right? So those two are important. Now, to know where the wavelength is on the longitudinal wave, it will be the exact point in a rarefaction to the next point in that adjacent rarefaction. So we notice if we use the middle line here on the rarefaction and to the adjacent one to it, that is one wavelength, right? It's not just the rarefaction. We look at the compression. So if we say the third one in the compression, which is right here, so the adjacent other compression, the third one in it, which is at this point, these two lines, X and Y, we measure those distances, it will also give us the wavelength of the longitudinal wave, right? So it's just to identify a common point in a compression to the next common point in the adjacent compression, or the same for the rarefaction to the adjacent of the rarefaction. So that's how you know the wavelength of longitudinal waves. Our question, yes, condensation is another term used for compression in the longitudinal wave. All right. Now, another thing to note with the lines that are used to create the longitudinal waves, these lines are known as your wavefront. Right. So these long, straight, parallel lines are called wavefronts. Right. And these they are just another way of representing the wave. All right. So that equation is not important at this level. So we're going to skip that and that one as well. All right, so that's the basics of waves and types of waves. So now let's look at the phenomena that waves actually undergo. So these are things that each wave, depending on the type of wave, will actually undergo. So the first type is the reflection. So all waves will be reflected, meaning that when it hits a border, it's going to bounce off from that border. All right, so that's what reflection is. Now, if it's a reflection on a smooth surface, then we actually have two laws that govern that specific reflection. So just an example, if we have light being incident onto a mirror, right? So we notice that there is a light particle or a light wave that is coming into the mirror here, and that's known as your incident ray because it's going towards the boundary, right? And then it's being reflected or bounced off on the next side, which is known as your reflected ray. All right, so these two terms are important. The incident ray is the one going towards the boundary. The reflected ray is the one coming away from the boundary. And we also see that between the reflected and the incident ray, there is also a dotted line here, which is known as your normal. Now, the normal is a 90-degree line drawn to the boundary or the surface that your ray actually hits. So at any point on the border or the boundary where the rays hit, you will draw a 90-degree angle to the surface, and that gives you your normal line. So your normal line is important because that's the line of reference that you'll measure your incident angle and your reflected angle. So if we look at the right side, we see theta I, which tells us that is your incident angle, which is from your normal to your incident ray, right? And then theta R, which is your reflected angle, which is from your normal to your reflected ray. So it's important to know it's between your normal and your rays, because sometimes CXC will normally try to trick you by giving you an angle like this and say this is 30 degrees, right? And they ask you what's the angle of reflection, right? Now, we notice if this is 30, remember the normal to the surface is 90, so therefore your incident angle will be 60 degrees. All right, so that's something key to note, that your angle of incidence and reflection is always from your normal to the respective ray. All right, so that is reflection. Now let's look at the two laws that governs reflection. So the angle of incidence is equal to the angle of reflection. And that's only possible if the surface is a flat surface, a flat, smooth surface, right? So once it's a flat, smooth surface, then the angle of incidence is equal to the angle of reflection. Now, if the surface is rugged, then that means each angle will be different. So your incident angle will be different from your reflected angle. The next rule of reflection is that the incident ray, the reflected ray, and the normal ray all lies in the same plane. And by plane, I mean, notice if you draw a graph, you talk about your x-axis, your y-axis, right? And if you go further, you'll hear about your z-axis. So because all these lines can be drawn on a paper, just like how we did here, that shows that it's just in one plane. So it's either in the x plane or it's in the y plane. So that is what it means, that all the lines that are drawn, the reflected, the incident, and the normal lines are in the same plane. So those are the two rules or laws of reflection. All right. Now, it doesn't only happen with light rays, it happens with any rays. So if we notice, we have a wave in a string. All right, so you just attach a string to, let's say, a wall, and you're moving your hand up and down to create a transverse wave. So when that wave hits the wall, it's going to actually, you're going to see the wave bouncing off from the wall back in the same direction, coming back to you. All right, and that's also a form of reflection. All right, so that is reflection. All right, and then the next term here, so the next phenomena that waves undergo will be refraction. Now, refraction is the bending of a wave when it enters a next medium. So if it's traveling in one medium and it's going into a next medium, then the wave will actually bend, right? The degree in which the wave bends is actually known or given by the refractive index of that material, right? So if we look at this figure here, we have an incident ray coming from medium 1, all right? And if we notice, when it's going into medium 2, it changes its path. So that means it is bent, right? So if it was supposed to continue straight, right? If it was supposed to continue straight, then this would be its normal path. But because it's changing medium, right? And that means the end value of those mediums are different. So this N1 value is different from this N2 value. Then it changes its path, right? And now it's no longer continues in that same path, it gets a new path, and that is refraction. Now, the degree in which it refracts, as I said, it's dependent on the N value, and N there is your refractive index. All right, so let's see. So consider straight water waves passing from deep to a shallow water. Their wavelength becomes shorter. Well, however, it must be noted that although the wavelength is shortened, the frequency of the wave remains the same. Since V is equal to lambda F, it means that the wave travels more slowly in the shallow water than in deep water. And that's something to remember in terms of refraction of water. All right, so, and also refraction in general. So in refraction in general, shows us that the wavelength will change when it moves from one medium to the next, right? The frequency is constant in refraction, so the frequency doesn't change, and also the speed changes from one medium to the next. So two things changes in refraction: the wavelength and the speed of the wave. The frequency remains constant. All right, so refraction of light is the reason we see phantom images when a straw is placed in a cup of water. All right, so if you notice in this cup of water here, when you look at it, it shows like the straw is actually cut when it's in the water. You're seeing two paths there for the straw. right? And that is the phenomena of refraction, right? And just like looking at things in the water, where it actually is compared to where you see it at, you notice on the right-hand diagram, the brick is actually lowered down in the water, but when you're looking at it, because the light rays that are actually leaving your eyes and going to the object, it actually bends when it reaches the water because it's changing from air to water. So it actually gives the image a little bit higher than it is actually is. Again, we have laws that govern refraction. So the first law states the incident ray, the refracted ray, and the normal ray all lies on the same plane, right? Just like the reflected law. And the new law, the second law, is known as Snell's law, which is named after Wilbur Snell, which was a scientist that did a lot of research on refraction. And his law states for waves passing from one medium to another, the sign of the angle of incidence and the sign of the angle of refraction are in constant ratio. And that constant ratio he noted as the refractive index, right? So the refractive index, N, it actually tells you how much degree a wave will be refracted when it's in that specific medium, right? And a common one that everyone knows is the refractive index of air, which is 1, right? And we know refractive index of glass is 1.5, right? But these are normally given, right? But most persons want to remember the refractive index of air, which is just 1. And also refractive index is a dimensionless quantity, so there's no unit. And that's because if we look at this here, we're dividing two of the same quantities, right, which has the same unit, so therefore both units will be canceled. We have no units for the refractive index. Also, the refractive index can be found by dividing the speed of light in air divided by the speed of light in the medium that you want. All right, so if you want to find the refractive index in glass and you have the speed at which the wave is of light passing in glass, you divide it by the speed of light in air, which is 3 times 10 to the 8 meters per second, and you will get the refractive index of glass. All right, so is that clear? All right, great. All right, so this table shows you a little bit of some common objects, medium, and their refractive index. All right, so let's look at light waves moving into a faster medium. So a faster medium meaning that the refractive index is less or lesser, right? So from medium 1 to medium 2, medium 1 has a higher refractive index than medium 2, right? So in this case, so this is N1, so N1 refractive index is greater than N2. And in that case, the wave, when it enters N2, it will actually go bend away from the normal, right? So we get a greater bending of the wave away from the normals, right? So in this case, your incident angle, which is theta I, will be less than your refracted angle, which is theta R. All right, and now for the next one, this is where N1 now has a smaller refractive index than N2. All right, so in this case, the theta or incident angle will be greater than your refracted angle. All right, so once your refractive index is greater than the next, then if it's going to that medium that is greater, then that means it's going to bend towards the normal, because that high refractive index value tells us that it's going to actually bend the wave greater than the previous medium. All right, so that's what the refractive index is all about. All right, and again, please note that the angles of incident and refraction are between your normal and your ray. So it's not between your boundary and the ray, it's always between the normal and the ray. All right, so with refraction, there is a case in which at a point of incidence that your ray, instead of going to the next medium, it can actually stay inside the same medium that it's in, right? So if we look at that diagram there, we see that wave is moving from water to air, right? So we notice the first diagram on the left shows that we have refraction because it passes from water into air, all right? Now, the middle diagram here, we see that there is a condition where we see theta c, and theta c is known as your critical angle, right? And what your critical angle tells us is that at this angle of incidence, your wave will no longer actually refract, but it will tend to want to reflect, right? So if it's at the critical angle, instead of it passing to the next medium, it's actually going to bend on the board of the boundary between the two mediums. So that's what the second one is. And then the last one here is where your incident angle exceeds that theta c, which is your critical angle. And now we have the ray, instead of passing to the second medium, it actually reflects back into the first medium, right? And in that case, that reflection inside the first medium is known as total internal reflection. It's total because all the wave is actually sent back in the same medium, right? And it's reflection, meaning that the angle of incidence equal the angle of reflection. So theta 1 equals theta 2, right? So we get total internal reflection when the angle of incidence is greater than your critical angle, right? And an equation that we use to find the critical angle of a medium is that sine c is equal to, and if it's air and a next medium, it's 1 over n. So the 1 here represents the refractive index of air, and the n here represents the refractive index of the medium in which you want to find a critical angle for. C, we know, is the value for the critical angle, right? But if it's two different mediums, so let's say we're looking at water and we're looking at glass, right? So in that case, it's not 1 over n. So if it's a medium that doesn't include water, air, sorry, right? Then it's the refractive index of the lower value, so let's call this NL, over the refractive index of the higher value, let's call it NH. Right, so that is actually the general formula of finding the critical angle of a medium. So sine c is equal to the refractive index of the lower n over the refractive index of the higher one. So because air is the lowest possible refractive index, once air is present, then it's 1 over n. All right, is that clear? All right, good. So the principle of total internal reflection is actually utilized in the telecommunications industry. It's used in what is known as the fiber optic cables, right? So these are the cables that are used to send high-speed information, so such as for networking, the Wi-Fi connections, all those things use fiber optic cables, right? And what these cables are is it's just a basically empty space inside these cables where the signal is actually reflecting when it's traveling throughout that specific tube, right? So the to get the consistent reflection inside the tube, it's actually, the cable is actually padded outside with a very thick coating of insulation to ensure that none of the wave is actually refracted, but all the wave is actually reflected inside. All right, so that's one use of the total internal reflection. Also, you can use it in endoscopes, which are the things used to see images inside your body. All right, so those are refraction, right? And then the next phenomenon that waves undergo will be diffraction, right? And diffraction means now if you have a border, but on this border you have a gap, so that means the wave is not going to reflect, but now it's going to actually pass through that opening or gap. When it passes through the gap, it's going to spread, right? So it's going to cause the wave to spread out, right? Or some persons will say to cause it to curve, right? Or deform. So it spreads out the wave when it passes through an opening or a gap inside a boundary, right? So the degree in which it bends, it's dependent on the size of the opening. So if it's a small opening, then it spreads it a lot. If it's a wide opening, it spreads it at a small degree. And that's what we see. So in figure A, we see that because it's just one side of this boundary here, then only the top part of your waves are actually bent. Sorry. Now for B, we see that the gap is a relative big gap here. So we have a small portion of spreading of your wave, so the waves can pass through that gap. And then for the C, we see that the space in there is very small. So that means your waves have to squeeze through that spacing, which will cause it to actually spread out more. So we get that oval shape of our wave passing through. All right. Now on these diagrams here, if a question asks you to find the wavelength from a diagram that is drawn to scale from a wavefront, right? So these are the equally parallel lines away, then the wavelength of these waves would be the distance between the two parallel lines. So that's the wavelength, because each space in between these wavefronts are the same value or the same space. So therefore, from one line to the next gives us the wavelength of the wave. All right. So no question, does diffraction only happens with longitudinal waves? No, it doesn't. It actually happens with both types of wave, longitudinal or transverse waves, because transverse waves can be drawn as using wavefronts as well, right? So that is, so both types of wave will undergo the diffraction, right? So, so the longer the wavelength of the wave and the narrower the spacing that the wave is passing through, the larger the amount of diffraction. This property is the reason why we able to hear sound around corners. Right? So the wave will actually bend and spread around the corner. So that's why when someone is, let's say, at the front of the house and you're at the back, you're able to hear the sound. Because every small opening the waves will pass through and will cause it to spread out so you can hear after. All right, so characteristics of diffraction of waves. The frequency, the wavelength, and speed of waves do not change. So nothing about the wave changes. So frequency, wavelength, or speed, those things will not change. Change in the direction of propagation, the pattern, the amplitude of the wave decreases, so its energy decreases. All right, so only the amplitude of the wave changes, right? So the amplitude of the wave will get smaller because it's going through a gap. So basically, that gap will cut off some of the amplitude of the wave. All right, so the last one, which is interference. All right, so the time, we have 1 minute. So we're going to restart and then we start with interference for the last one. All right, so let's look at interference now. So interference now is where two or more waves will come in contact with each other, and that contact will either create a larger wave or a smaller wave, right? So it's the combination of two or more waves to create a new wave, and that new wave can be smaller than the original waves or larger than the original waves. So depending on which one is larger or smaller is dependent on the type of interference that will occur. All right, so the two types of interference is the first one, which is their constructive interference, which means that these two waves are actually connecting with each other and they are in phase. And remember, in phase means that the similar point on one wave meets the similar point on the next wave. So if we look at the diagram here, we have the crest of the first wave joined with the crest of the second wave, right? So that means that it's constructive, they are in phase, right? So if we're supposed to draw a line through these waves, right, it passes directly through the same point on both waves, so crest to crest. And if we look at the troughs as well, we see that both troughs connect as well. So because we have the same points on both waves connecting together, it creates now a wave that is bigger in amplitude than the first two waves, right? Now, we have different degrees of constructive and destructive interference, but we're only going to focus on when it's completely in phase. And completely in phase is this example here, where crest and crest meets and trough meet. And in this case, because the amplitude of the first one was A, the amplitude of the second one was A, when we get a new wave, now it's 2 times A. All right, so we're adding the amplitudes together. And that's what constructive interference is. All right, and then we look at destructive interference. And destructive interference now is when the waves are out of phase. Right, so constructive when they are in phase, destructive is when they are out of phase. So we notice that the first wave, its crest, is actually meeting the trough of the second wave. And the trough of the first wave is meeting the crest of the second wave. All right, so in this case, again, they are completely out of phase. So in that case, because both waves have the same amplitude, we get a wave that is of no amplitude. So therefore, we don't get a wave, right? But depending, so let's say the second wave, instead of it having the same amplitude, let it say it had a 2A amplitude. So it's 2 times the first. All right, so question, so they cancel each other out. That's correct. So destructive, once the two amplitudes are the same and it's total and the crest and trough meets directly, you get a cancellation, so you don't get a wave. But let's say the second wave, instead of it being A, it's 2A, right? So in this case, you will get a wave that is of a A value, right? Because we're minusing the 2A minus the A, and we get A amplitude in our result, right? So we only get no wave when both the two waves that are there have the same amplitude, right? But once the amplitudes are different, then you just subtract both amplitudes, and that gives you the new amplitude of the wave that will be created. All right, so that's what destructive interference is. All right, so these just shows you different ways. So example of interference in everyday life is actually with sound, because it's actually seen mostly with sound waves. Now if you have two speakers, right? Now you notice that when you have speakers being posted for like persons having an occasion, the speakers are normally set in a specific position. If they're set to a specific position, you're going to hear a disturbance, a squeaky noise, right? And that squeaky noise is actually because the two waves are combining in a destructive manner, right? So that's why it's turned in a way. So what you're doing is actually changing the path of the waves so they can meet each other closely, so we can get a constructive interference. And when we get a constructive interference, you hear a louder sound than if it was just one speaker. All right, so let's see, so let's look at this. So let's say S1 and S2 are two speakers, right? Because the waves now will intersect and connect, so we get interference, right? If you're going to, if you're walking in front of these two speakers, you actually, if you listen keenly, so if this is a line that you're walking from, let's say we're walking from this side going up, what you will actually hear if you're a keen listener is that at each section, so at different sections on this path that you're taking, you're going to hear a louder sound and then a softer sound and then a louder sound and so intervals of louder and softer sound, right? And that's because in this scenario, you're having cases where you have constructive and destructive interference, right? So, so that's why, but in most cases, in reality, you don't hear the soft and the loud because you're just focusing on the sound being produced. But if you listen keenly, you will actually hear the distinction in a loud and then a softer and then a loud and then a softer as you go across that path. But exactly in the middle, that's where you will hear the loudest sound. So exactly between both speakers, that's where the loudest sound will be produced. So the further you go away from the center, right, the sound decreases, right? So, so that's what interference is about. All right, so is that clear? All right, great. All right, so we're going to look at one last thing here about waves, all right, before we do any question, which tells us about the experiment done to prove that light is not just a particle, but it's also a wave, right? And this was taken from a scientist, Young's, which is known as your Young's experiment. So Young was a scientist that wanted to prove, because most scientists back then thought that light acts just as a wave, just as a particle, sorry, rather than a wave. Right? So Young's actually came up with what is known as Young's double slit experiment, right? So he had this experiment where he had a light source, right? So he had a light source, and behind the light source, in front of the light source, sorry, he had a slit that had two small openings there, right? And that's why it's called a double slit, because it's two slits that are there. Right, so this is our slit, right? So we know if light acts as a wave, right, then that means if it's passing through these slits, what will happen? So when light passes through these slits, if it's acting as a wave, then something will happen. What's that? It expands. Someone, any other? All right, so that's the only option. All right, so I think I know what you're saying when you said expand. What I think you mean is that it will spread, right? And we know spreading of the wave is actually diffraction, right? So we have some of the wave will pass through the first slit, which is noted as the black marker here. So we're going to have the spreading of the wave, so diffraction here, right? And then we still have light going through the second slit, which is our red marker. We're going to have the second slit having spreading of the wave as well, right? Now, what do we notice with these two waves, right? So these two waves now, they are connected, or they are combined with each other, right? And when two or more waves actually connect with each other, then we have interference happening, right? And we note, with same as the speaker, he placed a screen in front of his double slit here, right? And he noticed that on his screen, he saw patches of bright and dark colors, right? He noticed that in the center was the biggest bright color, right? So the biggest bright, and then going away from it, started to see that the brightness starts to fade, right? So he started to see fringes. So these things are called fringes. So alternative dark, bright on his screen, right? And the only way you can have dark, bright on a screen by light is if we have interference, right? So because we had interference from just one light source, so that means when the light passed through the two slits, they actually spread and they actually connected and interfered. So we had two things here. We had diffraction of the wave and we had interference of the wave. So because we had those two things, then Young could have actually concluded that light actually acts also as a wave. Now, let's look at the reason why we have areas of bright and dark fringes. Now, sometimes CXE will ask you, could you identify where a constructive interference will happen and where a destructive interference will happen? Right? So remember these parallel lines here. So these lines represents the crest. Right? So those are crest. The space between it will be troughs. Right? So we have the red crest going that way, and we have the black crest going that way. So that means the areas where two lines meet would be a constructive. So we put a C here because the black and your red line meets directly there. So that shows us that there's a constructive interference happening there. If we don't want to use the lines, we can use a space. So we have a black space here. So between these two lines, a black space. Between these two red lines is a space. So here we can have constructive right here as well, because it can happen between crest and crest or trough and trough. And destructive now would be anywhere where just one line is. So destructive, this is just one line there. This is just one line there. This is just one line there, one line there. All right? So those are the areas where constructive and destructive will occur. That gives you the areas of bright and dark fringes. All right, so is that clear? All right, great. All right, so let's look now at some questions. All right, so let's see. All right, so let's look at this. All right, so question 1. Suppose that a longitudinal wave moves along a slinky at a speed of 5 meters per second. Does one coil of the slinky move through a distance 5 meters in 1 second? Justify your answer. All right, so the speed of a wave actually tells you the speed in which the energy is moving throughout that specific wave, right? So that tells you how fast the particles are vibrating basically every second. So in this case, because our slinky is actually acting as your medium, right? It actually tells you that it's moving 5 meters every 1 second for one coil of your slinky spring that is there. All right, so that statement is true. All right, so give one example of a transverse wave and another of a longitudinal wave. All right, so that's your question. Give me one example of a transverse wave, light waves, all right, and one longitudinal sound wave. Great, because sound is the only one you should know at this level. All right, question 4. What's a period of 60 Hertz electrical power? All right, so we know that we just get our frequency because frequency is measured in Hertz. So we have our frequency asks us to find a period. So the relationship between period and frequency is that period capital T is equal to 1 over F. And F here is your frequency, right? So basically we will have 1 over 60, right? And in that case, we get 16.7 milliseconds, which is the same as 0.0167 seconds. All right, so that's a popular equation. So the only two equations that are used by CXE for waves is that T is equal to 1 over F and V is equal to lambda, right? So this section only requires a lot of reading and just remembering these two popular equations. All right, so question 5, find the frequency of a tuning fork that takes 2.50 times 10 to the negative 3 seconds to complete one oscillation. All right, so it's because it completes one oscillation in that time, that means that's our period, and it's asks us to find frequency. So therefore, frequency is equal to 1 over your periodic time, 1 over t. All right, so if we put 1 over 2.50 times 10 to the negative 3, we get 400 hertz. All right, so the same thing will be done for question 6 as well. Same 1 over f equation to find. So 1 over t again to find the frequency of question 6. All right, so let's look at question 9. So it says wind gust creates ripples on the ocean that have a wavelength of 5 centimeters and propagate at 2 meters per second. What is their frequency? All right, so that's where the second equation comes in that says V is equal to lambda f, right? So asks us to find frequency so that we make f the subject. So frequency is equal to speed over wavelength, right? So we put our speed, which is 2, over the wavelength. Now we notice the wavelength is in centimeters, so we convert to meters by dividing 5 by 100. So we get 0.05, right? So 2 divided by 0.05, and we get 40 hertz. All right, so are those calculations okay with you guys? All right, great. So it's just to remember those two equations for any of these calculations for pertaining to waves. All right, so let's look at the wave phenomena, reflection, refraction, and those things. All right, so it says speakers in stereo systems have 2 color-coded terminals to indicate how to hook up the wires. If the wires are reversed, the speaker moves in a direction opposite that of a properly connected speaker. Explain why it's important to have both speakers connected the same way. All right, so giving you some time to think about that and then tell me what you think. All right, so anyone thoughts of it? All right, no answers. All right, so all right, there's one. So if the wires are hooked up properly, then more destructive aren't hooked up properly, more destructive interference will occur than constructive. And that is true. All right, so not connecting them properly, meaning that the signals will actually be going in opposite direction, right? And in opposite direction, when they actually interfere, you're going to have more destructive interference, causing you to get basically a very low sound or no sound at all. All right, so that's what it's saying. All right, so let's look at these and see what will happen with these waves. All right, so A. So it's moving from a less dense medium to a more dense medium. So would we have it to be going away from the normal or towards the normal? Towards. Great, so it will change its direction going closer towards the normal because it's in a more dense medium. Our next one, B, more dense to a less dense medium. So therefore it will be refracted away, right? So you have a higher angle there. And all these are just the same, right? And notice that the refracted rays are actually on the opposite side of your normal, right? So some persons probably will have that as a refractive ray. That's not the case, right? All right, so now let's look at some, all right, so here we go. So it's asking us to find the angle, the refracted angle, if we have our incident angles and each refractive index. So let's just do 2. All right, so I'm going to need you with calculators because I don't have one right now. All right, so in refraction, right, once you talk about refractive angle, there's only one equation that should come to mind, which is Snell's equation, which is says that N1 sine I is equal to N2 sine R, because this is the only equation in terms of refraction that has the refracted angle R in it. All right, so let's do part A. So substituting N1, N1 will be the refractive index of the medium where it's coming from, and it's coming from this one here, which is 2.34. So that's N1 for A, right? So that is N1, then multiply by sine I, and in this case, the angle of incidence in A is 25 degrees. So we add sine 25 equals to N2 is the refractive index to the medium where it's going, and in this case, it's the 1.24 sine R. All right, so you're going to help me to calculate. So calculate the left side and tell me what you got. All right, so the left side, we get 0.8989 equals to 1.24 sine R. All right, so we're going to divide each side by 1.24. All right, so we get sine R to be, what's the answer there? When we divide by 1.24, we get 0.798. And in order to find R, right, we have to sine inverse the 0.798, sorry. So therefore, R is equal to the sine inverse of 0.798. So therefore, angle here given will be 53 degrees. All right. So let's look at how you can just look at it and know if your answer is somehow right. Remember what we did before? We say that if it's a less dense medium, so the more dense medium will mean that the refractive index will be higher than the less dense medium. All right, so this case, this one is the less dense, this is the more dense medium. So if it's moving from more to less, then that means it's going to go away from your normal. And away from the normal would mean that it's going to have an angle that is greater than 25 degrees. And we notice that our refractive angle is 53. So that proves that your steps were correct. All right, so now I'm going to give you the chance to do B. All right, so do B and tell me what your angle of refraction is. 17 degrees. All right, let's see if someone else gets that. 16.7, which is 17. Great. All right, and as you know again, it's moving from a more dense medium to a less dense. But if you notice, it's slightly different in the refractive index. So that's the reason why the refractive angle is slightly higher, right? And if you notice, this one is actually increased by one or more. So that's the reason why this is far away from 25. But this one is very small, is 0.2 difference. So therefore, your angle created will be slightly bigger than 15, and in this case will be 17. All right, so that's the process of using our Snell's equation to actually calculate the refractive angle. All right, it can be used to do the opposite of calculating the refractive index or the incident angle, depending on what the question asks for. Now let's look at finding the critical angle. All right, so in this case, we're going to find what the critical angle is. All right. Now, the first thing though is 30 is asking in which setup is the correct to give a critical angle. So which one is labeled correctly in order to label as the critical angle? So it can be more than one answers or one. So from A to D, which one of those setups have the correct labeling for the critical angle? So A and B. All right, so A, B, and also for D as well. Right, so A, B, and also D. All right, so we have the normal, the incident angle, and the angle is between the incident and the normal. So that also is correct. All right, so now for 14, we find the critical angle of each of the situations. All right, so let's do part A. All right, so remember critical angle is sine C is equal to the refractive index of the lower one, so let's call it NL, over the refractive index of the higher one, let's call it NH. All right, so for the first one here, it would be sine C would be equal to the lower one, which is 2.33 over 3.45. All right, so therefore, when we find that and find C, we get 42 degrees. All right, and we remember that this angle here tells us that if the angle of incidence, which is this angle here, if it exceeds this value, 42 degrees, then the ray will not refract, meaning it will not enter medium 2. It will reflect, meaning it will continue and stay in medium 1. All right, so that's what that value tells us. So if a question asks if a ray will be reflected or refracted, then the first thing you'd have to do is to find the critical angle. And then from that, you compare it to your incident angle to see if it's greater or not, and then you'll know if it will be reflected or refracted. All right, so that's the same process you do for B, C, D to find the critical angle. All right, so now we're going to do one last calculations, which is this one, and it's not really a calculation. So explain why the ray of light does not change direction at D and at F. All right, so let's go with that answer. All right, so we notice that the ray is hitting, let's do D first. So the ray is hitting the boundary AB at an angle of 90 degrees, right? So that means your incident angle is equal to 90 degrees. Now, if we're supposed to draw a normal on this diagram where the incident angle is, the normal will actually be in the same line as your incident ray. And that's because if your incident ray is 90 to the surface, right, then that means it's equal to your normal, which is always 90 to the surface, right? So in that case, sorry, this incident angle is not 90. It's now will be 0 because it's the angle between your normal and your incident ray. So your eye will be 0 degrees, right? And based on Snell's law, because it's moving from one medium to the next, and we're going to say this is medium air, it's moving from air to glass, right? So therefore, N1 would be 1. So that's 1 times sine I, and I here is 0, right? And it's equal to N2, which is 1.5 for glass, sine R. So we need to know what's the refractive index of R. But if we put sine 0 in the calculator, you're going to get 0. So therefore, this is 0, right? And if we divide by 1.5, it's still 0. So therefore, if we find sine inverse of 0 to find R, we get that R is equal to 0 degrees. All right, so that's the reason why. Because R is 0, then that means it doesn't change direction. So the incident angle equals the refracted angle, meaning you get a straight line from air to glass, right? And also from when it comes from E towards F, it's the same. So we get an angle of 0, so we don't get refraction, so it continues straight throughout, right? B, state one property of light which does change at D and at F. So which property of the light changes when it is at D and F, and that obviously will be the speed of the light, all right, because it's changing medium, so it's moving from air where it's fastest to a glass where it's going to slow down, so the speed of the wave will change, all right, and also we know that the wavelength of the wave also changes with diffraction. So any of those two will be an appropriate answer to give once you're talking about diffraction of light entering from one medium to another medium. All right, so that's all for this part of wave, right? It doesn't get any harder than this. All right, so is there any question before we look at the last part of this section of the syllabus? All right, so now I'm going to actually go through the last part of the syllabus of section C, which talks about lens. All right, so this is something that is popular, especially if you do bio. All right, so lens. So in terms of lens, a lens is a transparent material which causes the direction of light rays to change. All right, so that direction change can define the type of lens that is present. Right, so we have two main types of lens, which are the concave and the convex lens. Right, so how do we know which diagram is which? So we know one looks like this, and we know one looks like this one. So the first one here, A. Which lens is A? It's a concave, right? So this, once it bends in, that's a concave lens, right? And another term for concave lens is actually diverging, which actually describes what the way the lens does to light rays when it passes through it. So when light rays passes through a concave or diverging lens, it actually spreads the rays apart from each other. Right? So that's why it's called a diverging ray, a diverging lens. While the convex, which is called the converging lens, and converging means that light rays passing through, it converges it at a point, meaning it actually bends it towards a common point there. All right. So those are the two types of rays of lens, popular types of lens that we have. Now, we know that our eye has a specific lens, right? But sometimes that natural lens is defective, and so you have an eye condition, which is long-sightedness or short-sightedness, or you have astigmatism, right? Now, we use the different types of lens to correct our long-sighted and our short-sightedness disorder. Now, if you have short-sightedness, then what happens is that your natural lens in your eye is actually too strong. The muscles there are too strong, so it's causing the rays to actually bend the light. It causes the lens in your eye to bend the light before it hits the retina. Right? So this here is your retina. That's where the rays should be converging towards. But this here, it converges it before it reaches the retina. So that is called nearsightedness. So to correct this, right, then we need to ensure that the rays actually spreads out a little so they can converge at this point. So in that case, we correct nearsightedness by using a diverging lens. because we want to spread it out a little bit more before it's converged at the retina. All right, so this does the diverge to spread it out more. So when it hits your natural lens, that natural lens can converge it directly on the retina. Now with long-sightedness, this is where your eye actually gets smaller, right? So instead of the rays being converged onto your retina, it actually converges behind the retina. And this is farsightedness. So to correct this now, we need to ensure that we get more converging happening. So that means our glasses that we have are converging lens. So therefore it actually makes it come together before it hits your natural lens. So your natural lens can focus it on your retina. All right, so those are the two types of lens that are used based on the defect that you have far or nearsightedness. All right. Now, based on your lens, there are certain terms that you need to be aware of. All right. So let's just draw a converging lens and talk about those specific terms. So the first term is a virtual or an imaginary horizontal line that is drawn directly in the center of your lens. And that is known as your principal axis. So this is your principal axis, which is a horizontal imaginary line drawn through the center of your lens. Now we have another line in the center of your lens, but this time it's a vertical line, right? And this now is called your principal plane. So it's just a virtual line drawn vertically throughout the center of your lens. Where those 2 points meet in the center of your lens, this is called your optical center. And the optical center of your lens is the point in which any light that is sent in this section, it will not change its path. So there will be no diverging or converging of the light once it passes through your optical center. All right. Now, if we have a ray that is going towards this here, it will be converged. Right. Now, the point in which the ray is converged or concentrated is known as your focal point. Right? Or some books will have it as principal focus. So your focal point is the point in which your rays are concentrated after passing your lens. Right? And then the final, well, we have two more terms. We have a vertical line through your focal point, which is called your focal plane. And then the distance between your principal plane and your focal plane, that is known as your focal length. So your focal length is between your principal plane and your focal plane, or some books will have it between the center of your lens, which is your optical center, and your focal point or your principal focus. So those are the specific terms that you need to be aware of. And also, in terms of length, you have one equation that is important, which states that 1 over f is equal to 1 over u plus 1 over v. So let's see what the u and a, u, v, and f means. So we know the f here is your focal length, right? So it's 1 over your focal length is equal to 1 over the u here is the distance of your object. So let's say we have an object right here, the distance of the object away from the lens, that is u. Right? So that's your object distance. Right? And then where the image is formed is where the light is concentrated. So where the image is formed, right? So this line continues here, and let's say the image is formed right here. So that distance from the lens to the image is the V, right? So U is your object distance, and V is your image distance away from your lens, right? That's the only equation that is used in terms of lens, all right? So those are the types of lens, the uses of the lens, and and in terms of lens, we have images being formed, right? And we have two types of image. So either an image is real or it is a virtual image. So a real image is an image that can be projected onto a screen for an audience to see. So just as the image that is projected from a projector or from a laptop, right? So those images that are created there are real images. Virtual images are images that we're not able to get that image to be projected onto a broader screen. So images created by like a mirror, sorry. So like a mirror, that the image created there is a virtual image, right? So that image is not able to take the image from your mirror and project it so a bigger audience can see it. Now, an image can also be an upright image, right? So the images that are created in a mirror, a plain mirror, they are upright. So just as how you're standing and looking in a mirror, that's how the image actually is. So it's not upside down, right? So it's always upright, right? So if it's not upright, then the next term is an inverted image, right? But mirrors do not have inverted images, all right? The size of your image in a plane mirror is the same as your object size. So it doesn't get magnified, right? So it's the same as your object, right? So that means that if we need to find magnification from a lens, then your magnification from a lens M is equal to U over V, right? So the V over U, your image over your object. So if you have the distance of the image and the object, or you have the height of the image and the object, or the size of the image and the object, you divide the image by the object and you get the magnification of that specific lens. All right, so that's all that the wave section offers. All right, the last thing before we look at a past question, a past paper question, is to actually explain the reason why the word ambulance on the vehicle at the front there is actually written in that, in terms of if you look directly on it, it's written backwards, right? So it's not written in a visible manner that you can stand in front and read it from left to right. So it's written backwards, right? But anyone knows the reason for that? I know. All right. So the reason why it's written in that manner is because, all right, so someone says this so that the driver ahead of the ambulance can read it correctly in the rear view mirror, and that is correct. But why does your mirror change the direction of the letters in the words to make it correct when you use it, right? So the purpose is actually to ensure that the mirror that you're using on your car that's in front of the ambulance will actually read the words correctly. The reason for that is, remember when we talked about reflection, we say that the angle of incidence is equal to the angle of reflection. All right. Now, if I'm just going to use just a three-letter word instead. All right. So let's say we use top. All right, top. right? So this is a normal spelling of top, but if we look at, so you have a glass mirror here, and you're looking like this to the image of the word pot, because we need top instead of pot. Then what's going to happen is that the incident angle that's created by each letter, right? So in this case, this is the mirror that I have. All right, let's do it over here. So this is your mirror that you're looking at, right? So the angle created by pot, by the P to my I, is smaller than the angle created by T to my I. So that angle T is greater than the P. So because it is greater, then it's actually, I will see that letter first, right? So continuing O, and then we get O, and then finally the smallest angle, which is P, right? So that's what you see when you look through a mirror. And if you notice, once you look through a mirror for anything behind you, it's actually you're seeing the left side on the right side and the right side on the left side. And that's because of the angle of incidence being hitting the plane mirror that you have, that will actually cause you to see a change in the sides on the object or the image that you're looking at. All right, so that's the reason why it's actually written like that on the ambulance, and I think on police cars as well, or any of those emergency vehicles. All right, so we have 15 minutes, so we're going to continue with some questions. All right, so I think we did these questions, and all right, and we finished right at wave side, which is, yes, we finished at question 26 the last time, so we're starting at 27. All right, so which of the following waves has the greatest amplitude? All right, what's the answer we get here? Which one has the greatest amplitude? Oh, C. All right, great. So C is our answer, greatest amplitude, because that's the maximum point from your undisturbed position. All right, 28. Which of the following would be the basic difference between a transverse mechanical wave and a longitude mechanical wave? So one is medium through which they travel to the direction of vibration of particles in the medium 3, the wavelength. The important part here is the basic difference. Or B, which is 2. Yes, that is correct. All right, 29. Which of the following diagrams would represent the wavefront after reflection? So we notice the wavefront is curved going towards the boundary. So when it's reflected, how would we see that? B, A. All right, so it's A. All right, so when it hits bent going towards, it's going to reflect going bent the opposite direction, because it's going in, then it's going to come back out. All right, 30. The wavelength of a wave is changed during which of those phenomena? All right, so I have C and A. All right, so wavelength. So we know reflection doesn't affect the wavelength, so that's out. We know interference during wavelength is not affected in interference, so it's either with refraction or diffraction. So we know that in refraction, it's the speed of the wave is affected as well as your wavelength, and the frequency is unchanged. So therefore, it is C. All right. So C will be the answer there. All right, 31. An echo is quieter than the original sound that produced it. This shows that compared to the original sound, the echo has a, so if it's quieter, then that means which part of a wave is affected by the loudness of a sound? A. Great. So loudness has to do with amplitude. So that means if it's quieter, then it has a smaller amplitude. All right, 32. The following are types of radiation in the electromagnetic spectrum. Which of the following could have a wavelength which is greater than 1 meters? A. All right, let me see. Give me a moment. Radio waves. Yes, that is correct. All right, 33. Diffraction is not normally observed with light because C, the wavelength is very small. B, the light is not bright enough. All right, so it's not, the light is not bright enough. If you remember when we talked about diffraction, we said two categories or two criteria that will determine how much it will spread. It will be the gap, the size of the gap, as well as the wavelength of it. All right. So that means if we don't normally see, then that means the wavelength is very small for light rays or light. So that's the reason why it's not normally observed in light. All right, 34. Upon which of the following would the position of an image formed by a plane mirror depend? The distance of the observer from the mirror, the distance of the object from the mirror, angle at which the image is viewed. All right, so which one of those affects the position of your image in the mirror? Or B, which is the distance of the object from the mirror, which is correct. All right, so that's the only thing that affects the position of your image from a plane mirror is just the distance that your object is from the mirror. Every other things are not a factor that determines the image. All right, 35. Which of the following diagrams best represents the passage of a beam of light, white light traveling through a triangular glass prism? All right, so we notice it's arriving at an angle, so we're going to have refraction. So that means A would not be an answer because A shows a straight line. All right, so B shows that we have refraction. All right, let's look at C. There is bent, there is refraction, and D, there is a straight line. So it's not D, so it's either between B and C. All right, so see the answer is changing to C. All right, and it's actually C. All right, because it's going to a more dense medium, so it's going to refract closer to a normal. So the top ray that's refracted will actually come closer down, right? And then when it's exiting the mirror or the glass, it's going to actually exit at a greater angle, right? So that at the top angle there shows that it exits at a greater angle, so therefore C is the most appropriate answer there. 36. Which of the following statements are true of a diverging lens? 1. It is thinner at the center than at the edge. 2. It can form only inverted images. 3. It can form only real images. 4. It can form only diminished images. All right, so someone said C, which is 2 and 4, which it can only form inverted images, and it can only form diminished images, and that's a diverging. All right, and that is true. Wait, no, that's not true, sorry, because point 1 is correct. It is thinner in the center than at the edge, right? Oh, I rubbed it off. This one that was here, right, from our first diagram. So 1 is a part of the answer. So therefore C is not the answer. All right, so would we change? So, all right, so remember inverted means that the image will be upside down. Real image means that it can be projected onto a screen for other persons to see. which is true. So 3 is a part of the answer, right? So does it always produce inverted images? No, it doesn't. So therefore, it's 1 and 3, which is A. All right, next, 37. The diagram above shows the formation of an image by a. So what object would form an image where the object and the image is on the same side of the lens? And we notice the object is smaller than the lens, than the image, sorry. So which object will produce that? D, magnifying glass. Yep, that is correct. Right? Because the magnifying glass is the object is on the same size as which you see the image, and the image is always bigger than your object. 38, which is a section that we have not yet reached. So that's where we stop for today. All right, and we're on time. All right, so thanks guys for watching, and I'll see you guys next time. All right.